In part 1, we showed that a characteristic function of any infinitely divisible distribution can be represented by this formula here for some constant gamma, non-negative constant sigma, and for some measure mu on the real line without point 0, such that the integral of x squared truncated at 1 with respect to this measure mu is finite. And as we said before, you can also write these integrals over the whole real line, and the 0 here was excluded just so that this representation is unique. And here we want to show that all such functions of this form correspond to some infinitely divisible distributions. Of course, in the above representation, many parts of the representation should be already familiar to us. Okay, the first term it gamma just corresponds to a constant gamma, it's just a characteristic function of this constant. The second term minus t squared sigma squared over 2 just corresponds to a Gaussian random variable with the variance sigma squared. And then in the last integral, we are going to break it into the interval between -1 and 1 and the complement. And in particular, on the complement of that interval, that part of the integral above is just the integral of e to the itx minus 1. So the indicator disappears. And also, by our assumption, the measure mu on this complement is a finite measure, right? Because we truncate at 1, so outside of that interval we just integrate 1. And of course we have already seen what this corresponds to by the Campbell's theorem. Namely, if we consider a Poisson point process with the measure mu just restricted to the complement of this interval -1 to 1, the random variable given by the sum of x's in this Poisson process has such characteristic function. And finally, the only new piece that we haven't seen before is the integral between -1 and 1. And so we have this integral between -1 and 1. Now we exclude the point 0, and then we integrate e to the itx minus 1 minus itx, and here I don't need to write the indicator since we're already on that interval. Okay, now to simplify the notation, let's just first agree that the measure mu of 0 is 0, so we don't need to exclude the 0 from this interval. And also, not to write the interval all the time, let's just assume that mu, or redefine mu to be this measure mu restricted to the interval between -1 and 1 from now on. And in order to understand what kind of random variable this integral corresponds to, let's decompose the measure mu into a purely atomic part, let's call it mu1, and a continuous part mu2. In particular, mu1 will concentrate on at most countably many points, let's call them xk, with the weight of course will be just the weight of measure mu on xk, and let's denote those by delta k, okay, for some either finite or countably infinite sequence of points. And mu2 will be a continuous measure, okay, or non-atomic measure on this interval between -1 and 1. Okay, and we also decompose the above integral into the two corresponding pieces. So the first piece will be just a sum over these points we evaluate our function at this point xk times the mu of xk. And recall that this integral is inside the exponential, and if we look at this series here, we will recognize that this function corresponds to a characteristic function of the following series, okay, at least formally. If you take the sum over k of xk times nk minus xk times this measure mu of xk, k where nk is a Poisson random variable with the mean mu of xk. Okay, then for each term in this formal series, the characteristic function will be exactly of the above form. Right? The constant xk times mu k just appears there in front of it, and then the characteristic function of the Poisson is exactly of this form. Now, of course, in this sum, we assume that all these Poissons are also independent. So the characteristic function of the sum will be a product of characteristic functions, just like above. Okay, so this series formally matches this function as its characteristic function, and so we just need to notice that this series is indeed well defined. And first of all, for each term, notice that it's exactly centered. So the expectation of xk nk minus xk mu of xk is 0. And in order to apply Kolmogorov's theorem to show that this series converges almost surely, we want to see that the sum of variances is also finite. And then if you look at the variance of the above term, right, that will be exactly xk squared times the variance of the Poisson, which is mu of xk. And the sum of all these variances will be finite by our assumption that the integral of x squared between minus 1 and 1 of our measure mu is finite, right? So we truncate it by 1, but here we are on the interval minus 1 and 1. And so the series here is just the part corresponding to the atoms of this measure mu. And so we see here that the term that we subtracted in the above representation, this term itx on the indicator between minus 1 and 1, which played the role of cancelling out the singularity at 0, here it just corresponds to recentering of these Poissons, right, to make sure that the series actually converges. And then the remaining part corresponding to the continuous part of mu, this mu2, will be just the above integral with respect to this measure mu2. So we need to understand what kind of random variable corresponds to the integral with respect to this continuous measure mu2. And again, let's remember that this measure satisfies this condition. And here we restrict ourselves to the interval between minus 1 and 1. Now let's take the interval between minus 1 and 1, excluding the point 0. And here I'm also excluding the endpoints minus 1 and 1 because our measure mu is continuous, so those points really do not matter here. And then I want to split this interval into a disjoint union of some sets separated away from 0. So for example, we can take these sets to be intervals of the form 1 over k plus 1 up to 1 over k on the positive side and just flip them on the negative side. So plus minus these intervals. And then I want to write the above integral as a sum over m of integrals over these intervals. Okay, and the reason I wanted these intervals to be separated away from 0 is because for each fixed m in this sum, we can now separate the two integrals. So we can write the integral of e to the itx minus 1 with respect to this measure minus it times the integral of x with respect to this measure. Now, we cannot do this for the original integral because the measure mu2 can blow up at 0, and that's why the integrand is of the order x squared near 0. But once we split the integral into this series like this, because each interval is separated away from 0, both integrals now are well defined. And again, in this representation, we can recognize what these terms correspond to. In particular, if we consider a Poisson process with the mean measure mu2 on minus 1 to 1, if we fix index m and then take a sum of x in this Poisson point process, which fall into this interval Sn, and then we subtract the integral over Sm of x d mu2. Then we know again by Campbell's theorem that the characteristic function of this first sum will be just the first integral above. And the characteristic function of the second constant is exactly that second term above. And so what we want here is that the sum over m of such random variable is well defined, or this series converges almost surely. But we know by the properties of the Poisson point process that these terms are independent over m, because they are expressed in terms of Poisson process on disjoint partition. So this is just a series of some independent random variables, and then we appeal to Campbell's theorem again, okay, which tells us that the expectation of the sum of x's inside one element of this partition is exactly this integral that we subtract. So the random variable above is centered, and the variance is given by the integral of x squared. Okay, so by our assumption, the sum of variances will be integral on minus 1 to 1 of x squared d mu2, okay, which it was of course bounded by the integral with respect to mu, which is finite. And by Kolmogorov's criterion, the above series converges almost surely. So in fact, this is a well-defined random variable, and its characteristic function, again by Campbell's theorem, will be exactly what we want. The sum over Poisson process corresponds to the first term, and the constant corresponds to the second term. So this means that we gave some concrete construction of random variables whose characteristic functions correspond to the parts of our representation. And we only need to notice that these random variables are indeed infinitely divisible. But this is completely clear because in this series above, we can construct a similar series corresponding to the measure mu2 over n and do this independently for different indices. And we can do the same thing above in the terms corresponding to the purely atomic part of our measure, where we can split each Poisson into independent Poissons by the stability property. So this finishes the proof, and we show that any function of this form indeed corresponds to an infinitely divisible distribution. And our final result in this section will be the following simple observation. Namely, if we have a characteristic function f of t of some random variable x, and it has a representation of the same form as we had above for infinitely divisible distributions. Okay, for some constants gamma and sigma, and the only difference here is that mu is not necessarily a positive measure, that mu can be a signed measure written as the difference of two positive measures mu1 and mu2, such that each of these measures satisfies the same property as we had before, right? Namely that the integral of x squared truncated at 1 with respect to the measure μj is finite. Then such representation is unique. Now the proof of this is really one line, so I'm not going to write this here. Simply, if you have two such representations, you simply rearrange by moving the negative part of the measure to the other side of the equation. And then you end up with equal representations for the proper non-negative measures. And since we already showed that such representation is unique, it really means that all the pieces have to be the same. And the importance of this result, which can be used in some exercises in this form, is that if your characteristic function has representation of this form, and the measure mu is not a positive measure, but indeed a difference of two measures like this, so it has this negative part, then we know that the distribution is not infinitely divisible. So this result will allow us to conclude in the exercises that certain distributions are not infinitely divisible. Okay, so this concludes this section, and in the next section we will discuss a special family of infinitely divisible distributions, the so-called alpha stable distributions.